So firstly, I want to say thank you, everybody, for joining this first IMS stream session for the virtual conference for UK this year. Nice to see some familiar faces and some new ones as well. So without further ado, basically, all of these sessions are recorded. If I've actually got everybody, you can unmute yourselves. Or you should be able to unmute yourselves if you want to ask a question. So I'm all for that. And Vivash says that's fine if you interrupt him in the presentation. So Vivash Sharma is from BMC Software, and he's going to do this presentation on unlocking the power of IMS shared queues, why they matter. So as I said, if you've got any questions you'd like to ask, then please unmute yourself and ask that question. So over to Vivash, thank you.
Thanks, Dominic. So welcome everyone. So I'm very excited to present the first session of IMS GS UK this year. So yeah, first I will start with my introduction. So good morning, good afternoon, and good evening, everyone. So before we start, I will give a brief introduction about myself. My name is Vaibhav Sharma, and I'm having 14 years of experience working with mainframe technologies. Currently, I'm working as a QA at BMC Software, focusing mainly on IMS sysadmin products. So today, I will be presenting on the topic shared queues and why they matter. So first, I will quickly go through what I will cover in today's session. I will talk about how transaction flows work in a non-shared queue environment. Next, I will cover the limitations of non-shared queue environment. And then we will see why shared queues are a better option. I will then talk about different queue types and key components in shared queues. And after that, we will discuss how to prepare IMS systems for shared queues and after implementation changes and how MSC fits into this setup. In the last, we will have a Q&A session. But if you have any questions during the presentation, you can put them in the chat. I will try to address them. Okay, so before we deep dive into shared queues, let's first understand how message queues works in a non-shared queue environment. In a standalone IMS system, IMS uses a queue pool of memory to store the input-output messages. Once this queue pool buffer gets full with messages, IMS uses DESD datasets to store the messages. There are three DESD datasets used in message queues: queue blocks datasets, short message queue datasets, and long message queue datasets. Now, suppose a user is sending a message from a terminal to a standalone IMS system. The input message will first come into the message queue buffer. Once the message arrives in the queue buffer, IMS will then schedule the respective transaction into MPR region to process that message. After the message gets processed, the output is put back into the message queue buffer, and from there, it sends back to the originating terminal. So in standalone IMS system, IMS has exclusive use of its own message queues. Here, message queues comprises of both the queue buffers and the DESD datasets. Now let's look at the transaction flow in non-shared queue environment. As you can see in the diagram, a user at terminal LTMZ is sending messages for transaction TranX. The message will first arrive in the queue pool buffer of the IMS. This standalone IMS, IMS2, has three dependent regions: MPP1, MPP2, and MPP3. So any dependent region which is available can schedule this transaction, TranX, and process the message. After processing, IMS will put the response back into the tuple buffer. From there, IMS will send the reply back to the terminal LTMZ. So here, MPR region MPP2 was available, so it processed the message. In a standalone IMS system, it's the user responsibility to manage the number of available dependent regions. So when message traffic increases, user can increase the dependent region to manage the traffic. Now let's move on to the limitations of standalone IMS message queues. As you can see in this diagram, each IMS, IMS1, IMS2, and IMS3 have their own separate queue pools of memory and message queue datasets. All the three IMSs are sharing the same database, but they are not sharing the message queues. So in such systems, workload balancing between IMSs becomes user responsibility. For workload balancing, a user can configure MSC links, which is multi-system coupling facility, or set up ISC connection between these IMS systems. Both approaches can get quite complex when the number of IMS system grows. Also, the complexity of maintaining such system increases as number of IMSs increases. Another important point here is that if the local message queue datasets are not sized properly, in that case, if there is a sudden spike of messages for a BMP application, which is in a bent state, in this situation, the message queue datasets can get filled up quickly, and this can lead to an IMS outage also. So managing separate message queues for IMS systems adds significant complexity and scalability issues. Now, next, we will see the shared queues, how we can address these challenges through shared queues. Okay. So what are shared queues? So shared queues are set of input-output message queues that can be accessed by multiple IMS systems operating in a parallel sysplex environment. In a shared queue setup, input-output messages queues are not stored locally on DESD datasets. Instead, queues are maintained in list structures on the coupling facility. Any IMS that is part of the shared queue group and has available resources can pick messages from these structures, process them, and put the response back into the structure. In shared queues, DESD datasets and queue pool queuing function are replaced by message queue structures in the coupling facility. In shared queue environment also, all individual IMSs will have queue pool buffers. Individual IMS will first receive the input message in queue pool buffers, and when complete message is received, IMS will move the message into the shared queue structure in the coupling facility. So till the messages are in the queue pool buffers, they will be part of the local queues only for that IMS. But once the messages are in the shared queue structure, any IMS which is part of that shared queue group can process that message. Now let's see why shared queues matter. So shared queues supports automatic balancing and routing of messages among multiple IMS systems. Without shared queues, we would have to manually configure MSC links between individual IMS systems to balance the workload. Shared queue environment also allows for incremental growth. As the workload increases, we can add new IMS systems without disrupting the existing lockdown users. For example, if a banking application experiences a surge in traffic, we can bring up new IMS instances having no terminals or users connected to handle this additional workload. Once the workload decreases, we can make newly added IMSs down without impacting any existing user. So up to 256 IMS systems on 32 ZEOS images can be combined to process a single workload. Another major advantage is it improves availability and reliability. Suppose an IMS fails, then its workload can be processed by other IMSs in the shared queue group. Messages on the shared queues are never lost, even if we cold start one or all the IMSs in the shared queue group. If we compare this to a standalone IMS message queue, in that case, a cold start will lead to loss of all the messages on the queues. So in that case, a system admin has to manually take a dump queue, snap queue checkpoint before shutting down the IMS system. And then later, he can restore the message from the IMS logs using those checkpoints. Okay. So this diagram shows that when multiple IMS systems running in parallel sysplex environment shares databases, message queues, and VTEM generic resource group, then the end user will experience that they are interacting with a single unified powerful IMS system. So it provides a single system image to end user. Now we will see how a transaction flows in a shared queue environment. In this picture, you can see the three IMSs, IMS1, IMS2, IMS3 are part of the shared queue group. And all of them are connected to the message queue structure in the coupling facility. As you can see, the terminal LTERM Z is connected to IMS1. And if a user is sending a message for transaction TRANX, IMS1 queue pool will receive this message and will write it to TRANX queue in the shared message queue structure. When the message arrives in the shared queue, notification will be sent to all the IMSs in the shared queue group to see which IMS is interested in processing this message. Suppose IMS2 has its MPR region available for processing. So IMS2 will pick this message and will process the message. After processing, IMS2 will write the output back on the LTERM Z queue in the shared queue message structure. When output message arrives in LTERM Z queue, another notification will be sent to IMS1 to pick the response from the LTERM Z queue and deliver that response back to the terminal LTERM Z. So in this shared queue system, we receive the message through IMS1, process it through IMS2, and deliver the output back to the originating terminal through IMS1. In short, we have replaced the individual message queues of each IMSs with a common set of shared queues. There are two sets of shared queue structure in shared queues. One for full function messages and another one for fast path messages. Message queue structure, which is for full function messages, contains multiple input queues, like separate queues for transactional messages, serial transactional messages, and suspend transactional messages. Similarly, there are separate output queues for messages to terminals, PPC application, OTMA clients, or a remote MSC link. Inside message queue structure, we have two additional queues for long messages, which we also call as staging queues. We have one staging queue for large transaction messages and the other staging queue for large LTERM messages. Similarly, EMH queue structure, which is for fast path messages, also has two separate queue types, one for input messages and another one for output messages to LTERMs, logical terminals. So in this picture, you can see different queue types available for full functional messages in shared queues. So here you can see that we have, as I have told you earlier, that we have local queues also for IMSs in the shared queue group. So This picture is showing both the shared queues and the local queues. Now let's look at how messages are stored in shared queue structure. Both input-output messages are stored in shared message queue structure based on their queue types. The shared message queue structure are list structures in coupling facility. The list structure will consist of multiple list headers. Each list header depicts a specific queue type. There will be list headers for transaction messages, LTM messages, OTMA messages, and other queue types. The messages that are associated with these list headers are called as list entities or messages. So now we will see what components are required to implement shared queues. First, we need to define list structure in the coupling facility. For full functional messages, we define a message queue primary structure and an overflow structure. Defining overflow structure is optional. Similarly, for fast path messages, we define the EMHQ primary structure and an optional overflow structure. If our IMS system doesn't have any fast path application, then the EMHQ structures are not required. Next, we define two logger structures in coupling facility, one for message queue structure and other one for EMHQ structure per shared queue group. These logger structures are critical in recovering the shared queues in case of any failures. These logger structures are also defined as list structures in the coupling facility. We also need a separate address space called CQS, which is a common queue server. CQS acts as an interface between IMS in the shared queue group and shared queue structures. CQS handles all the activities of queuing and retrieving messages from the shared queue structure. Each LPAR requires one CQS, and multiple IMSs on that LPAR can connect to the same CQS. Then we define the CQS checkpoint datasets, one for the message queue structure and the other one for the EMHQ structure per CQS. So for every CQS, there will be a message queue checkpoint dataset, separate for message queue and EMHQ structures. So these system checkpoint datasets are used for CQS restarts in case of any failures. Next, we have two structure recovery datasets, which we also call as SRDS. Also one for the message queue structure and other one for the EMHQ structure per shared queue group. These SRDS datasets, along with the log structures, are important in recovering the message queue structure in case of any failures. Then we have log streams defined inside the coupling facility within the logger structures. There will be one log stream for message queue structure and the other one for EMHQ structure per shared queue group. CQS uses these log streams to record all the activities on the message queue structure and the EMHQ structure. All CQSs within the same shared queue group uses the same log stream. When these log streams become full, they will be automatically archived to the logger spill datasets. Similar to how it's done in standalone IMS system, where olds are archived to slits. These log streams also plays an important role in structure recovery and CQS restarts, ensuring message integrity after system failures. Now we will look into how we can implement shared queues in our IMS systems. So the good part is that no IMS gen is required to implement shared queues. The first step is to define the necessary structures in the coupling facility. We've already discussed about the structures in the previous slides. In addition to that, we need to add a few new members and update some existing members in the IMS proclip library to enable shared queue functionality. We also need to define a proc for the sequence address space, which acts as an interface between the IMS and the shared queue structure. So now we will look into the utilities which we require for defining the CFRM policy and the coupling facility structures. So we use IXCMIAPU utility to define the CFRM policy and the required coupling facility structures. Once the coupling facility resource management policy is defined, we can activate it by running the command set XCF start policy. On this slide, you can see a sample JCL to define the CFRM policies and for building the shared queue structures. We use the same utility to define the logger structure and log streams. So here is the sample JCL for the same. We use the IDCAM utility to define the CQS system checkpoint datasets and the structure recovery datasets. These are sample JCLs to define them. Okay, so this is a sample proc for setting up the CQS address space. Okay, so now we will look into how IMS transaction management works after migrating to shared queues. So when you bring your IMS up after implementing shared queues, IMS connects to the shared queue structure through CQS. Once the connection is completed, IMS register interest in specific queues. So register interest means IMS is capable of processing messages on that queue. Okay. So for the how IMS register interest. So for the input queues, IMS will register interest in input queues for transactions that are defined and are currently active in that IMS. If the transaction is in the stop state, then IMS will not register interest for that transaction. Similarly, for the EMH queue input queues, which handles fast path structures, the fast path transaction must be defined and scheduled in the IFP region before IMS can register interest. For output to logical terminals, LTERMs, IMS will register interest in output messages for those terminals where it has an active session. It's important to note here that multiple IMS systems can register interest to process an input message, but only one IMS, the one in session with the terminal, will register interest to deliver the output message. Okay, so now let's talk about how MSC multi-system coupling facility fits into a shared queue environment and how we can take advantage of both for workload balancing. Okay, so if you look at this diagram, you can see there are two shared queue groups. Notice that there is no MSC link between IMSD and IMSC in the lower group and IMSA and IMSB in the upper group. However, IMSC is connected to remote IMS, IMSR through MSC link CR. And IMSB is connected to remote IMS, IMSR through link BR. But here's the interesting part. Even without a direct link, MSC link, both IMS A and IMS B can still send and receive messages from remote IMS, IMSR. Why? Because in a shared queue group, any IMS can use the IMSC connections of any other IMS in the same group. For example, if a transactions arrive at IMS D will put that message into the shared queues. Then IMS C can pick this message and send the message to the remote IMSR for processing through MSC link CR. Similarly, IMS B can receive messages from remote IMSR and place it into shared queues. And IMS A can pick this message and then process this message. Also, one big difference in shared queues is that the concept of local system ID changes. Normally, in a traditional MSC setup, every IMS needs a unique system ID. But in a shared queue group, the local sys is shared among all the IMS systems in that group. So if you have 3 IMS systems and only one of them has real MSC link, then you only need one system ID for that IMS. And the other 2 IMSs will share that system ID. So in this way, configuration becomes easy, and we can take advantage of both MSC and shared queues for workload balancing. Okay, so now let's look at some other benefits of MSC with shared queues. Suppose if we want to add a new remote IMS to one of the IMS in the shared queue group to scale our IMS systems. So in that case, we need to perform IMS gen of only that IMS. And there is no need to perform IMS gen of other IMSs in that group. So this means we have to do a plan outage for only single IMS, and all other IMSs in the shared group remains unaffected. Also, when we add a new IMS to the shared group with its own unique MSC resources, there is no outage required for any existing IMS members in the shared queue group. Every IMS stays up and online while we scale up. So in this way, by using MSC with shared queues together, we can increase the capacity of the shared queue group to process MSC messages and improve availability for remote IMS system to access the shared queue group. So that brings us to the end of my presentation on IMS shared queues. So we have seen how shared queues simplify workload balancing, improve system availability, and makes IMS environments much more scalable and resilient. So we have around 15 minutes now, so I will take any questions.
So Vibhav, thanks very much for that. Can I just ask a question about when we define the actual shared queues themselves, can we have 2 sets of shared queues? Because if a shared queue actually is that not a vulnerable area if that was not available? So if the structures were not available, is there ways of defining the structures in a way that makes them more available, or could we have 2 sets of structures and use those?
So Dominic, you mean like 2 sets of message queue structures?
Yes.
Okay.
is that something that people have to consider, or is that not?
Okay, so you are saying like in this standalone IMS system, like we increase the number of DSD data sets in case like we want to increase the message queue storage. So it's the same way like we have in the shared queues also. You are asking like
Yeah, I mean, it's in a shared queues environment. Is there any vulnerabilities with having a shared queue message structure? And is there a way of actually increasing that availability is what I'm asking. Yeah.
Okay, so that like we have to like that system admin has to take care like while he is like defining the size of the those structures. So he has to keep those size large enough like so that they never get full, and like in case like if they get full, there will be a overflow structure like which will support the uh, messages in case like primary structures are like in some overflow state. So in that case, overflow structure will work.
Okay. Yeah. So that's for
So
handling the messages. Yeah. The throughput.
yeah.
Yeah. Okay. Have we got any more questions? Please shout up. There's a few of you
Yeah,
on the call, so
yeah,
if you've got any.
yeah, Vaibhav, this is Vikas here. So there is a question came to my mind that if I am supporting 3 to 4 IMS systems, and if one or more than one IMS system fails, that is placed in a shared queue, so will it still be processed by the remaining one? Because at that same time, if I check it, there are loads of queue and which are more at that time, which resulted in a long contention. So what need to be addressed for queue processing at that time?
So Vikas, your voice was not clear, but still I will repeat your question. Like what I understand, like you are saying that there are multiple IMSs and they are sharing. They are using a shared queue, and if one
Yes.
of the and if one of the IMS fails, so in that case, there is a contention in the queues.
Yeah, if one of the IMS is failed, so and at that same time there are loads of queues which resulted in a long contention. So will it still be processed by the shared queue?
Yeah,
Uh,
so in that case, like other IMS systems will take that load and like will process them. So for that, like the transactions like should be defined in all the IMS systems.
yeah, that is fine. If suppose there are 3 systems only and 2 of the system fails, and if only one system is there, and there is a loads of queues on that one single system, so how that shared queue will be processed at that time?
Okay. So yeah. So in that case, like for the if single IMS system remains, so like in that case, like we have to increase the MPR regions, like so that to accommodate uh, processing of the messages. So we have to increase the MPR regions for
Okay.
that single IMS. Yeah. So it's not like that, like if we have defined shared queues, like everything will get resolved. Like, so there will be a system admin role also, like he has to think about like how like he can manage like the processing part of the messages and the uh, queue part. So yeah. So for the shared queues also, like a system admin has to like define the size, has to decide like what size of structures he should build in the coupling facility, and how many MPR regions like a single IMS should have. So such like you have said, like in case like if there are 3 IMSs and 2 IMS system fails, and there is load on only single IMS, so in that case we have to increase the MPR regions.
Okay.
And I guess it'll be used in the offload a lot, won't it? if you've got a lot of transactions coming in, and it's say a 4-way plex, and you're only actually got one side of the plex up, and as you said, numbers of transactions need to be able to cater for the number of regions for those transactions, and then also like what you were saying before about the offloading components come into play as well.
Yes. So
Thank
yeah,
you,
it will.
Vaibhav.
Yeah. Thanks, Vikash.
So we've got any more questions? Just shout up. Okay, so that's a bit of a pause there. So we've had a few questions there, but thanks very much for doing that presentation, Vaibhav. And I know everybody that these are recorded. So I did say that at the beginning, I think. So I know some of you joined a little bit later. So these recordings should be available after this presentation finishes, and you should be able to play that back at some point in the future with a link. And that link will get externalized at some point in the next few days to enable you to do that. But thanks very much everybody for your attendance. There's about 20 on the call, so that was really good. And we look forward to everybody joining some of the other sessions we've got planned. We've got another four presentations today, so hope you're enjoying this one, and we'll take a chance to look at some of the other presentations on offer. Thanks very much, Vivash, for that. And I believe there's also, if you want feedback on these sessions, you should be able to do that. I think should be a QR code, but we might not have that on the slide, but you should be able to do that by logging on and doing your feedback. When you're registered, you'll be able to log on and actually give that feedback for any of the sessions. So without further ado, I'll say thanks everybody, and have a good rest of your day. Thank you.
Thanks everyone for joining this session.
Thank you. Thanks, Vivash. That's appreciated.
Thanks,
I'll end the session there. So technically, I do have to end the whole session now. So thanks, appreciated.